I think everything is set up. Yeah, it looks like everything is indeed set up. Don't know why things keep messing up. Very strange. Yeah, the code set up here doesn't... Don't know why it's not stable. Anyway, hopefully it doesn't affect us. Hopefully the rain won't cause us trouble. Let's go ahead and... Let's see here, where are the ads? What does the ads look like? Or currently have an ad... Actually, can I pop this out now? No, I cannot. What are they? Anyway, let's just... We're just going to go ahead and start. Oh, I'm an eye. There we go. Okay. Oh, I don't know why. I really don't. But for some strange reason, Twitch, a lot of the stuff that I used to use for Twitch, the different managers and such, they don't seem to be working right now. Maybe it has to do with my setup. All I know is that I can't really see when ads are going right now, and it's very annoying. Either way, let's go ahead and program. Let's get to programming and get this done. So last time on stream I was... Oh, there's an error. Oh, okay, alright, yeah. Okay. Alright, so last time, when we were streaming, I was over here messing with a lot of the layer to frame code, trying to get things situated and figured out, and I've actually kind of finished it. I ended up finishing it over the weekend. Pretty much what's going on now. If we look... I wrote it up so that now we have the variant processing, dynamic processing, static processing. And then we also have a separate little micro function for processing the images. The idea here is to try and shrink things down a bit. Yeah, it looks a little hacky, and the reason... I should probably actually put down a note here. So let me actually put a note here so that I will, when I get back to this, I'll be like, why is it doing this? So, there we go. Alright, so yeah, so I have set up the code for auto cropping, and by doing so, what this allows me to do is shrink down the images to their bare bones. So now, if we go over here, this is what the original data looked like. If you hop on in and go, you can see it's a fairly big size, because originally this was just supposed to be something super simple, just overlay as much as possible. Don't have to worry about any kind of calculations. And I kind of worry that because of the size of because you can see this is actually a relatively large image. And loading all of this, especially all of this empty space into memory, might not be the most efficient way. Since, you know, we're trying to speed this up as much as possible. So what I figured was, hey, why not go in and start cropping all of these images? And by doing so, what will end up happening is it will allow me to shrink the size of all of these different, well, shrink the size of all these things that need to go into memory. So now, when you hop on over, let's go to Anger, we'll go to 4. You can see here are all the different layers. There's the arms, the body, the mouth, the tail, and then here are the eyes, the VR eyes, and the VR headset. And if you look here, I attached to all of these images a series of numbers. I did this largely because I couldn't really think of another way to do this, given that these folders all will have individual pieces in them. And if you look here, the sizes of these are all slightly different. I did think maybe of setting it so that each individual layer, for instance, like how the mouth would be processed, the body, the tail, these would all be cropped the same way. And by doing so, it would theoretically mean that I only have to store this information in the... I would only have to store this particular information in a config file. But then I thought it would make a lot more sense to auto crop it so that I get... So that it would... Because we're in a fight with memory here. The way I'm currently setting this up is that I just do not have enough memory. So if I can make these, the footprint for these as small as possible, that will make things a lot easier. We can just do the math. We'll just program it in to do the calculations. But the second thing is we're going to try and see if we can push this over to the GPU, because right now everything is being done by the CPU. Apparently, OpenCV, if we hop over to OpenCV, okay, not PySpark. Yeah, we're looking at that earlier. Let's see here. Yeah, I don't need that now because we're still using OpenCV. Oh, come on, OpenCV. How about we do this? Python OpenCV GPU. Aha, okay. Here it is. Oh, where is it? I saw it earlier. Actually, I'm a bit surprised. Well, I mean, okay. You can kind of see it here with the CUDA, Git CUDA enabled device. You can see it right here. But they actually... here it is. Upload CPU. Here it is, right here. Look at that. I can create a CUDA GPU matrix, then upload an image to it, perform the various calculations that I need, and then download it, as you can see right here, download later. That means if I can load all of my images into these GPU matrices, then I can have blazing lightning fast recompilation of all of the images and then pull them back out. So yeah, this potentially could help speed things up dramatically, which will be kind of what we were hoping for. So yeah, this is one of the steps I'm going to take. But then, yeah, this was one of the steps we're going to take. And from there, we can start seeing about what to do next. For now, though, we need to start fixing Framer. Because we're going to be switching over. Yeah, so because we're going to be switching over from, we're going to do a full modification of Framer. The way that Framer works, the way how it was originally set up, yeah, this is going to kind of get gutted. So, yeah, this 160 lines of code is going to be turned into sushi. Because originally this was just going to be a basic container. The idea was that it would hold all of the information about what one would need to do, and then from there it would then pass all of that to pretty much load up all of the images on the fly. And if we weren't going to make any modifications, then it would just return an existing image. As you can see right here, we have an image file. If it doesn't exist, we compile, and then we'll return said image. So every time we don't make a change, then this frame should hold the memory. But yeah, we're changing this now. The framer is now going to be memory active. It will hold all of the information about the locations. It will hold pretty much the ideas that it will take all of this information, pull all of the data into it, to generate all of what we need, and then send it all to the GPU. And then from there, with the GPU working, every time we request for an image, for instance, I simply type, because if you go down here to compile images, you can see I put in the background color, I can say what type of variant there is. So we're actually going to change this up a bit. So now, This is actually going to be, instead of just a variant, we're going to make this a quar. Well, yeah, let's see here. Let's see here. Do I have a... Actually, before I start messing with Framer, we probably should go to the importers and start working with that. So right now I have the importer set up into two methods. I have the frame importer, which is where all of the individual pieces were separated out into individual layers. It pretty much was how we were originally doing things, but since I'm trying to save on memory and compile things more, it's kind of become more of a layer type setup, so I'm going to be working on the layer importer instead. And technically it's kind of a mesh between the two, so we might end up just cutting this entirely. But I digress. What we're doing now is we're going to work with this code here. So first here we need to find our, let's see here, let's get to the setup folder section here, and then we can start working on it. So this is our dictionary. All right. Let's see here. So when we were looking for the emotion side of things. Boop. Actually, let's see here. What does this look like? Ah, here we go. So lab coat. So we're technically looking for these right here, right? Another layer below. So let's see here. Ba, 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 ba. Of course, it's going to be false because if you look at the keys here, you can see it's just lab coat. So because this is not correct, we're going to go a layer deeper. So layer, which means we then pass through. So let's go ahead and grab our... since this is a loop, and plus we're just we just want to get to a spot where we can get some data. So next will be lab coat. So this is the layer deeper. And now we're here. This code should be active. So this should be true. Let's go ahead and generate our key and our layer. So our key is curious. Our layer is all of our information. And then from here, we then pass this into here. So now from here, set up folders. The layer folders is going to be layer. And then from here, let's go ahead and run that. So now we have our frames. There's 1, 2, 3, and 4. Nice. Here's our config. This is the general config, which contains all of our information that we need. We should probably load up the general config at this point. Yeah, we should. Largely because this is where we're going to be building the framer. You can see it right here. Here's framer. We're going to be building this here. So with that in mind, I'm going to... All right, well... And the internet dropped for a second. What? The weather in Hong Kong has been so bad. I do not know why the weather has been so bad, but it has been so infuriating because it drops. It's so annoying. It is so annoying. We're going to stream as long as we can, but if the stream suddenly just cuts out, yeah, that's because of the weather. And sorry about that. Anyway, so let's see here, because originally I was creating this right here. This right here is supposed to be the layers dictionary, and as you can see, yeah, as you can see here, this is a slightly modified dictionary. because originally this is what I was passing into Framer to get everything set up. So if you look, mouth actually now has a path layer, a modifier, and then a layer mode. The paths contain all of the different all of the sequences for. This is where all of the images are located. That's what those are. And then modifiers would be all of the different changes that we were originally going to do to said layer. But because we're not doing that now, and this is we're not really. I mean, I could still keep those in, but this way I could end up having the eyes be a different color. Like, oh, I want to have bright pink eyes, or I don't know. I could change the color of the t-shirt. You know, these kind of things. But yeah, we can. It'll be good to keep this here for the sake of modifying. Layer mode is something that's also is now very important, because the framer is no longer just going to. Because originally the way I was working was it was working off of two different parts. I originally had something called dynamic, and then I had something called static. Dynamic was what allowed to hop between the different arms. For instance, if I had my character, his arms are down. For instance, if my character's arms are down, if he's playing a game, arms in the pockets, up in the air, like, hey, check that. Man, the arms always look very weird when I do that. Look at that. I think I'm going to have to fix the arms a bit. I don't know what it is. Maybe it's because they're too long. I like the arms going up like that. And this is, yeah, I'm going to have to fix this. Anyway. Okay. Don't get distracted. But yeah, so because of that, that's what the dynamic was originally doing. And it would process based off of if a folder was input or if it was just a path. But we're not doing that now, because it is important to know the difference between a dynamic layer and a variant layer. So with that in mind, the first thing we need to do is we need to load the config. So we have our config file. So let's do config dict. This is going to be a dictionary with a string followed by another string. All right, and then we're going to do, let's see here. I wrote a JSON utils file. It should be, load JSON. So we're going to load the JSON configs. We're going to have to. I'm going to have to fix that. There we go. So here's our config dict. And here you can see there's our layer mode. Here is the overlay sequence, which is important. Background color, the shape of the image, and the frame rate. And these are all now very important information. And the reason why is because all of the images have been ultra cropped. So we now need to we need the shape. It's really important. And the layer mode is something that we're now adding as a way to define what's going on. So let's see here. So now we have this. The first thing we need to do is we need to process layer mode. So why don't we go ahead and do that? So we'll call this layer modes. And this will be a dictionary with a string followed by an animation, or this should be a layer mode. And then with that, K. Config dict.get Yeah, there's a lot of static stuff here, but let's just get this working right now. There we go. So now that we have our layer mode set up, there we go. Now with that in mind, let's see here. There's our mouth, our tail, our body, our VR. Yeah, that's one problem. Yeah, that's one problem. The fact that all of the stuff now has being tagged with the value, so we're going to have to do a little bit of processing here. It shouldn't be too hard. We have again, a lot of this is going to, let's just get it written. You don't need to be open right now. Give me more space. All right then. Let's see here. It's technically the key that we need to process, so why don't we call this the there we go. So we have mouth, tail, VR, eyes, body, eyes, VR. So how do we do? We can clean, because what we should do is we should do a basic cleanup for the keys. Because all the keys are really are this information. Actually, maybe we can do the cleanup for the keys a bit further up. Let's see here. That way it saves me time, saves me pain in setting this up. So it's this one right here. Or it's not that one right there. This should be this one. Hit enum if available. I'm busy looking. Where did that code go? Here it is. Here we go. Right here. Get file directory. Here we go. Get file directory. Get enum. Ah, right here. So dir temp path name. So yeah, this is right here. This is it. So let's see here. Why don't we call this the path name? Let's go ahead and get a key. Let's go ahead and get ourselves a key so we can do a, we'll call this path name. There we go. So we have path name. And what we want to do is we want to strip. It'll be a left strip. Anything that is okay, baby R strip. All right. So there's where we're going to... How about we do this real quick? Let's see. There we go, perfect. Let's do that. Actually, quick question. What happens if this is what happens if this doesn't exist? That I think I might find a bug. Okay. Because if I remember, find should... If I remember, find... Let's go ahead and just change it to that. Yeah, -1. Yeah, that's not going to help. Yeah, I have. Yeah, I was about to just induce a bug here. Yeah, okay, it would make more sense to do this. If, we'll call this the, we'll call this PP because that's what we're looking for. Or, okay, then this will be the. Yeah, I'm going to go with PP. We're looking for the PP. The tiny PP. Let's see here. Yeah, this would equal. This would definitely equal the. What we're going to call this path. Unresolved attribute find. In. Oh yeah, because this is a path, isn't it? So we'll go with stem. There we go. Okay, let's just go ahead and grab let's get the VR one. All right, so this will be our path. There we go. Now then, when we run this, it should give us a number. I wonder, can we do walrus? Can I do walrus and this at the same time? I don't think I can I? I'll be running this twice. Okay, why don't we do this? Greater than 0. So if this is greater than 0, I guess it's fine. It's fine. And we will go ahead and put this here. Why don't we call this name or stem? Then from here we can go path name. And if the path name has PP in it, then what we'll do is this to our path name or to path name dot find. There we go. So now if I run this code right here, path name should be fixed up, and then from here we can just simply right here, this bop and bop. There, perfect, good, done. I see, because originally I was looking for configs, but let's see, actually now that we're no longer doing that, I don't think I need this line of code anymore, since the configs are being processed slightly differently. Okay, there we go. So let's go ahead and rerun everything. There we go. Now that we have that, let's go ahead and run our code here. And we get an error. Okay, why are we getting an error? Oh, okay, it's because we haven't defined dict. Okay, there, we've defined it. Thank you. Good. We have our directory. Now then, we go in here, we can see VRI. Yep, perfect. Okay. Everything. Yep. That's good. Okay. Nice. Perfect. So now we have that. Let's see here. Now that we have that, everything is run. So now we just need to do is the next step, which would be locate the bottom. We already know what we're looking for. So why don't we just go ahead and here we go. Locate bottom. We already kind of know what we want. So let's just go ahead and layer folders this. And okay, what was this file called again? I forgot. It is a big file. What are you called? Data directory. Got it. Okay. Directory deck. Okay. And we will go ahead and get the lab coat. There we go. Now we'll want to get our animation. We'll go ahead and grab Curious, since that seems to be what's the one we're working with. Now this is our folders. This should be our folders dict. Our folder layers. There we go. So now with our folder layers, the first thing we do is we run this to find our configs. Oh yeah, I forgot. We're not done yet. Folder layers. We need to get, because we're running, I think there's a for loop. Yeah, here it is, a for loop. I actually need to grab 4. So this is technically the folder layers. And now we can run all of that. And no, we can't. Why are you complaining? None type. But all right. But there should be a config there. Ah, okay. This is where the general config's located. Got it. In other words, I was right earlier. Folder layers. So this should be where all of the configs are located. Why is it not finding them? Oh, I see. It's because we're missing the file name. Got it. That's a bit of some silliness on my part. Yeah, I'm parsing out, looking for the suffix. Let's go ahead and prefix that. Yeah, I should. Let me fix this. Here it is, this one. So yeah, we want to... Let's see here. Where was this located again? Yeah, this one right here. Path name. Yeah, so it was here. This one. If path is... Yeah, that's processing the path name. So we want to be down here, so... If path... Actually, you know what? Rather than engage my brain. How did I change this? Here we go, this one. There we go. There we go. Now I don't have to rethink about it. So yeah, the path suffix, if the path suffix is this, then we're just going to, you know, path dot name. There we go. Perfect. This is going to be very confusing. Path underscore name, path dot name. Oh. I wonder how many people will get confused by that. Okay, let's go ahead and reset this. Oh. There we go. There's our directory. Let's do a quick check to make sure that it has everything we want. Data directory, where are you? There it is. There's our lab coat. Idle. And yep, there it is. General.config. Perfect. Nice. Okay. Why don't we go here and see here. Folder layers. There we go. Now let's go ahead and load up our config and get our information. There we go. So there's that. Then here's our layer modes. And then from here, because the key is now correct, when we generate this, we can simply go layer modes dot get key k. So yeah, this is processing the frames. Let's set the frame to 04. That way we can get our layers. We can then do that. Name K is not defined. For K and V, K, V, there we go. And now with our layers sticked, here we go, right here, inspect. So now we have our path, we have our modifiers, and we have our layer mode. Here you can see this is dynamic, static, static, variant, static, static. So yeah, this, all right, yeah, that works out. That's perfect. So the idea, oh, and here's body variant. So the idea here is that those that are classified as variant, in this case you can see the body is one that is a variant. And then here we have statics, and then the mouth is dynamic. And the idea is that those that are considered variant, it will be processed slightly differently from those that are considered dynamic. Technically, they're all being held in folders. The reason why I set this up was to try and make things... I might be over-engineering it, but the main thing is that these would be processed slightly differently. The original idea was because, again, it all stems back to how I'm trying to store the data. Because eventually I might end up having everything stored in one folder with all of the different layers connected to each other. For now, we're still keeping it in frames, but anyway, that's why I have them separated. Whether it works or not, we'll find out. Whether it's a good idea, we'll find out. But now that we have the layer dict, we still do not have layer names. Alright, so how were we, when we originally were doing this, set up folder. Here we go. How were we getting the names? Layer names, layer names. Layers dict. Okay, where is layer names? Oh, apparently there's only one here. All right, where did the other one go? Okay, that's a bit... All right, maybe if we just look for the framer code here, we can see how we were doing it. It might be something that was much earlier. Here we go. So this is the code for the frame importer. Here we have framer, image manipulator. There's the dictionary. There's the image size. And then we just nope out on. Okay. Okay, apparently we just gave up on that. We're just not inputting in the names. Okay. Fine, fine. All right. Okay, we're not putting in the names. Let's see here. So, actually, yeah, that is fairly old code because we're not even doing this now. We're inputting in our layers dict. All right. So image size. This happens to be now also in our config. Let's grab that. Let's grab that. Config. There it is. Image shape. There we go. There's our image shape. Any other thing else that we need to put in Framer? Let's see here. Anything else? Up here to... Here we go. So image size, bit depth is fine. Mode is fine. Layer config, which was what we're passing in. We're not passing it... How did I process layer config? If layer config, then get overlay sequence. Okay, overlay sequence. All right, okay. So we were passing in an overlay sequence. Let's head back up here real quick. Let's see here. Actually, I need to hurry up, and that's a bot. We need to ban it. We need to ban bots. There we go. He has been reported. And he has been banned. Aha. There we go. Okay. I'll have to auto set that up. Yeah, I'll have to auto set that up. But anyway, let's get back to this. Let's see here. How are we doing this in Framer? Or in the frame importer? Once we get down here, I just pass in the dictionary, huh? Here we go. I see what's going on. I see what I'm doing. I see what I'm doing. What I end up doing is I prepare my, yeah, here you go. The overlay sequence and all that. I get it. I get what we're doing. Pop. So this happens to be the configs. The config dict. So if I run the config dict, there's our overlay sequence. Got a string / none instead. Well, but it's a list. I mean, I can see the list right here. Let's go ahead and run that. Boop. Let's see here. Overlay, overlay, overlay. Yeah, here it is. Overlay order. It's a list of strings. There's 7 in total. Very strange that it's not, yeah, very strange. Anyway. There we go. And then here is the layer component dict, which we pass on in. So let's see here. Now if I run all 3 of these, the final output for this layer component dict. There we go. So it's all now properly sequenced. The tail is first, the VR eyes is last. Let's see. We have our layer mode. There it is, our path, our modifiers, and our layer mode. And then we pass this directly in with our image size. So, okay, I think this is good. It looks like this will work perfectly fine. It will generate our sequence, it'll generate this here, and then it'll output it back out, and then it'll just kind of push it straight back up the path. Yeah, it should generate this and then push it back up in the path. So this is perfect. Oh yeah, this is perfect. All right, I think this is good. So now all we have to do is go start modifying Framer. So why don't we go ahead and start working on this? So self Framer. I think technically what I should probably, because right now everything is, you know, all of the requirements are it has a lot of requirements. For instance, we need to input in the image manipulation and we need to input in the path directory. These are 2 things that are extremely important. But I think that technically we can just build an empty one and then just start adding to it as we go. Plus, it could allow me a chance to start running all this code individually. Now let's see here. Where is this? Ah, here it is. I'm busy just taking a peek. Actually, technically, we can probably just run it ourselves. Let's just go ahead and run this. All right. Framer is going to be equal to self is going to be equal to framer, and we're going to bring in the CFI image manipulator, and this will be our layers component dict. Boom. Dict object has no attribute as POSI. Blah 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 blah. Okay. I am read. Wait, why are we reading? Wait, we shouldn't be reading anything. Oh, wait. I think I might know what the problem is. I think okay, maybe I don't. All right, maybe I don't. Okay, 1 second. Let me read this up here. Temp image manipulator. Load image. I don't know why we're trying to load. Oh, I know. It's because image size is missing. That's why image size is missing. So it's broken. All right, that is one thing where we are passing that in now as well. So go back over to importer. Yeah, we are running this now. I'm going to grab this. This should be able to run once because self is our... There we go. Okay. So now if we type in self, this should be our framer. Let's go over to our layers. There we go. There's all of them. All right, so far so good. All right, so let's get back over here to Framer and start messing with this. So the first thing is, let's see here. We need to update. It's not just Framer that needs to get updated, because we're technically using the layer components tab here. Here we go, layer mode. Actually, question. It looks like I already kind of programmed it in. I don't think we are passing it directly in, but you never know. I could have already done that. How about we do this? Let's go with self.layers.get tail. How about we get layers mode? All right, it says it doesn't have something. Maybe because I spelt it wrong. Layer mode. Okay, it should be just layer mode. There we go. And the tail is static, which is wrong. Oh, that is very wrong. This should be dynamic because it's a tail. The tail has multiple frames. In fact, I have a strong suspicion if we go into layers and check the path. Yeah, look at that. We have many. Oh, it's not ordered. Oh, it's not. Okay, it's not ordered properly, so we'll have to order it. Oh, I don't understand how these things... You would think that when it loads, there has to be some way that it's just loading up a directory. Maybe it has to do with how fast it likes to do the loading. Because it's never in order, no matter what. Okay, so let's see here. This image path, if it's a directory, if it's a path, we do this. If it's this, we need to... Alright, what I'm going to do, real quick, is fix this up. So, let's get the keys. This is going to be a K for K in which path, keys, and sorted keys. There we go. And then from here, we're just going to recreate our K and V value. Let's see here. KV for KV in the items. If K is, let's see here. Actually, if I remember, actually thinking about it, we just want K here. For K in keys. And then this will simply be image path dot get K. There we go. We've now sorted it and put it in image path. So there we go. This should help solve that problem. That way things will be sorted. Yeah, that way things will be properly sorted. Especially when it is these type of things. Then now here, go back over to importer. Not importer, framer. So here is where we're going to go through our values and our names. Image, here's our image layer mode. So layer mode types. What do we call this here? Layer mode types. Layer mode. Oh. This is where this is why I need globals. This is why I need a global key. Let's see here. Yeah, it's layer mode. It should be working. Okay, it should be... Okay. Hang on. It should be working, right? Unless I did something stupid in which our layer modes dicked. Let's see here. Tail. You are... Okay, why is tail static? Body is variant. Mouth is dynamic. Eyes is static. Okay, how much do you bet my config is wrong? Let's check out the... Let's check out configs dict. Actually, you know, it'd be faster just to go over here. Tail is static. Okay, yeah, I did. All right, yep. All right. It is working correctly. That's wrong. That should be dynamic. The tail is a dynamic structure. It's a different kind of it is. So let's go ahead and fix this all across the way. We'll just be quick about this. All right, since technically it's working and we have other examples, we'll just go run with those. But yeah, this is working. There we go. Okay. All right. Next. So yeah, our framer is working. It's going through. It's inputting in all the information. We now have our different modes and different stuff. So this means everything should technically be here. So now we need to... Now we can get... Maybe we can have a little bit of fun now. Because technically what I want to do is I want to... Instead of... Or image will be... It still will be the current image. But I want to get everything into memory now. So instead of everything just being stored... yeah, everything is being stored... Actually, you know what? Why don't we go ahead and go over to layer components. So we have our name, our path. We have a layer mode, visible. The layer location. Bottom layer... oh, the bottom left corner. Oh. Location. Yeah, we need to program this in. This is going to be from the processing of... It's this stuff right here, the PP. Yeah, we need to do that because otherwise everything's going to be put in the bottom left corner. So I'm going to assume that we did not... Yeah, we did not program anything yet. Everything is still set to there. So let's see here. Layer mode. So why don't we go ahead and put down layer location here as well. And this is going to be a list of ints. And this also will be equal to none. There we go. Okay. And then from... Alright then. Alright, let's see here. And then from here... Okay then. Oh, thinking. Thunk. By how I originally have it programmed, it makes more sense to set it up so that all of the variants and the dynamics are all in the same plane. Maybe I'll have to program it because this layer location is only set up for... Yeah, I might have to do that. Okay, we might have to... Let's... Alright, let's head over here. Let's head over here. So, layer to frame. Because originally I was just doing it very nice and simple, you know. Nice and quick. Just run straight through, process all the images, and be done with it. But since it looks like when we start working with the other ones... It looks like I think this is an issue with our... Technically is an issue with both variant and dynamic. As you can see here, we're busy going through grabbing these. So... The best, okay, the dumbest thing, but I think this might be the, okay, the best and the dumbest thing. I think that might be the best course of action, is to perform like the, well, we're going to have to auto crop. I know one way to do it would be to load all the images up. One way to do it is to load all the images up, collect where the autocrop would be located, pick the furthest points on all of them, and then go back through and process all of the images with said cropped format. That would require me to set up another way of doing the cropping. Because right now I have it from the side. I think that would be fine though. Actually, technically, I don't have to do the... image processing should be kept in the image processing area. I have an idea. All right. Technically, because we're working here, let's see here. This is the image manipulation code. We don't need that open. Layer components here. Layer location. We technically don't really need this. So let's see here. We have our name. We have our mode. We have our path. The path is going to be a list of all of the images into said path. So you can see them right here. So what we could do here is actually instead of... I have an idea. I had another idea, but instead I changed my mind. I have a different idea. Ideas aplenty. So this potential thing is, instead of... This will be a dictionary with string. But instead of it being a path, this will just simply be the location data, which would be a list of ints. Like that. And then from here, instead of processing it there, we process it here. So we're currently... Let's see here. So we have our sorted keys. There we go. We're going to put that back in there. Image path. And then self dot layer location. And this is just going to be a K. The V is going to be different, so we'll have to do that for KV in image path dot items. Now in this case, the V is a path. So what we want is the stem. And then... Actually, you know what? We should probably put this in a utils or something. Okay, let's go ahead and... I have JSON utils, I have global parameters. Alright then. Define... Okay, so here, well, this is... yeah, let's just go ahead and do this. Actually, if anything, since this is going to be a util here, where did we put that code? It should probably be in our layer to frame at the top, because that's where I was originally. Yeah, here it is, right here. This one. Go ahead and move this. There we go. And that way we can put this here. All right. And then now let's go back to our layer to frame. We need to import in the file. And then while we're at it, if I remember, is it here where we're processing? Here. This is importers. Okay, this one. There we go. Okay. And now that we have that, let's go ahead and get back over to our util strings. So first things first, we need to locate where this is located in our... Let's just grab one for now. We'll get the first one. We'll need to get the stem. All right, we'll call this the string. Oh. Fat fingers. There. Okay. So here's our string. So let's see here. We can go ahead and locate. Okay, we can go ahead and locate. So there it is, 2. So we'll call this the... So this is the start of it. So we'll call this the look, p-look. So it's simply that plus the length of our... There we go. So when I do that, this should now be 6. There we go. And then... There we go, and then the next thing we need to do. All right, so we'll call this the PP look list. And then we're going to simply return. There we go. Okay. So this should give us back out the numbers that we need. All right, so with that in mind, let's go ahead and grab this. Let's head over to here. There we go. Perfect. And this should be we want the stem. Perfect, perfect. There we go. And then that way we now have the locations of our files. We're doing this after we... Here we go. We're doing this after we do the... Well, yeah, we process image path. Then that way we can figure it out. And then we have all of the location information, which will be perfect. Because then when we start compiling it, we can start accessing that information. So first things first, let's go back to Framer. Here we go. Now, when we do compile image, where is our good old friend compile image? Here it is. I'm running overlay images. All right, so here is the composite image. Here is the image. All right, so overlay images. All right, yeah. It now okay, we know overlay images needs to have a position. So this should be the overlay position. So let's see here. Output generator. Here's our process. This is loading up all of our images. All right. So yeah, here's our output generator from loading in all the images. Yeah, you can see layer items. We might have to... Yeah, we might... Oh, actually, we're going to be modifying this code here a lot. Thinking. Technically, we need to start generating a lot of... Because ultimately what we want is this to be all stored on the GPU. So if we want this to be on the GPU and we want to be accessing it, then we need to be cognitive of where everything is. Let's go back to layer components. So here we have our path, we have our image, we have our layer mode, path, location. Part of me wants to make a pointer. Part of me wants to make a pointer and say this is where it's located in the GPU. Because if you remember, the way it works is we use, here you can see initialize the GPU matrix and upload data to VRAM. So here we create a GPU image called GMAT. We then upload our image. And then from here, we can then start doing a variety of things. Here you have the cv2.cuda converts, or CVT color. Oh, actually, I wonder. I see it's doing a lot of calls to the to CUDA. I wonder if this can be. Let's see here. OpenCV overlay to arrays. Because if I can just call, put the stuff into a image. Yeah, here we go. If I can just upload the images and then perform blending. I see alpha blend. But that's not what I want. I don't want to do alpha blend. But they do cv2.cuda. Okay, then, combine two arrays. OpenCV GPU combine two arrays. So here we go, GMAT. Here's... Sometimes you gotta hate the English language. Okay, then. Is there a CUDA version for CV2? Hey, Saura. Apparently there is. I was actually testing it earlier too. So import CV2, cv2.g. Let's see here. We were just looking at it. CUDA.gpu mat. This one. We'll call this A. There we go. So now I have A, which is now apparently a GPU. It's a CUDA element. So yeah, apparently OpenCV2 has... It uses CUDA. which will actually be helping me out a lot, because that means I can store a lot of the stuff onto the GPU and save myself up CPU space. Plus, it would actually help me a lot with, because I'm going to have a lot of calculations going on. For instance, like recoloring of images. I could be having them merging images together. I could even be doing things like affine transformations, which would be rotating the image around. And I'm going to be doing all sorts of weird things. Since this is the first time that I've been messing with this, I'm trying to figure out what can I exactly do. CUDA merge. And here, okay, here we go. Assuming A, B, and C are existing single channel GMATs, then I can do a CUDA merge and then combine them. Yeah, I'm trying to figure out what is available here. So OpenCV, GPU, probably should just say CUDA. Python, OpenCV, CUDA. Add 2 arrays. There we go. Add 2 arrays. I just want to know if I can do basic calculations or if there's something special I have to do. Oh, I can do add. That means... Okay, then. So here's D. So I see. So we add one, we add the other, we then put it into D result, which is what that is right here. And then I download from D result. Okay. Whoa. This is beginning to feel a lot like assembly. Like we're getting a couple points shy away from assembly here. Because in assembly, the way it works is, let's just open up an example. There we go. Assembly programming tutorial. Perfect. We're just going to... I'm actually a bit surprised that I don't see that this doesn't have anything. Thank you very much. You waste my time. I'm just looking for a basic example. Okay, here we go. Perfect. Yeah, here it is. Check this out. So here is this is how assembly looks here. If you look, you can see it has LDA, STA, LDA, and then a lot of other information. Let's see. Is add in here somewhere? The main point is that this is where it's being stored in memory. This is the memory location. This is telling you what you should be doing. This is telling you what variable it is. And then this is then telling you the next step. So the idea is, if you're going to add... Okay. I need to find the example. Assembly, add 2 numbers. There we go, perfect. Move here. So here you go. You can see the 2 right here. This is much easier. Oh, this is much easier to explain. Okay. So first things you have to do is you have to point what you're going to do. In this case, you're going to be moving to a particular location. Here it's EAX, and you're going to set the value to 14. You're then going to move to the next location, EBX, set the value to 10. You're then going to, because these are now 2 memory spaces, you're then going to add those 2 together. And then from here, you'll then push EAX, which means you'll then get the data, and then you will print it out. So you effectively define where you are in memory space, you define what you're going to be doing, and then you eventually get the data out. And if you look at what we're being recommended, we define our memory spaces right here. We then tell it a function, which is this, which is adding to adding, and then we're going to download it. This is effectively assembly here, just written in Python. Now, I guess this will be fine. So this does make things a little bit interesting because the way my image processor is working, or I should say my image manipulation code is working. Let's see here, because right now it's all done in CPU. I wonder if I could... Again, I'm wondering if I can just do basic calculations. Because I keep calling CUDA. I think it's just using CuPy. It might be using CuPy. In order to... Actually, you know what? Why don't we do a quick check? Let's do a... Alright, instead of just trying to get basics in from whatever AI this is, let's actually just go to OpenCV. Let's just go to its... I don't think it's that one. Here we go. Without seeing the error, it said that if you want to build against CUDA 20.8, which is released yesterday, you'll have to this should be able to build CUDA 12.3. Let's see here. Category topics. Pipeline. Okay, where's the API information? Well, that's the form, so... It is actually amazing that sometimes you type things in and it doesn't show you what you want. Open... Actually, maybe if I type in doc, it will actually give me what I want. Here we go. There's a... Oh... Okay, let's see here. OpenCV GPU module allows for CUDA runtime conversions regarding multi-threaded programming. This means the first API call for CUDA context is created implicitly attached to the current CPU thread and then is used as a current context of the thread. All further operations such as memory allocation, GPU code compilation are associated with the context of the thread. Since any other thread is not attached to the context, memory and resources allocated in the first thread cannot be accessed by another thread. Instead, for this one thread, CUDA creates another context associated with it. In short, by default, different threads do not share resources, but you can remove this limitation by using the CUDA driver API. You can retrieve context reference for one thread, attach it to another thread, and make it current for that thread. As a result, the threads can share. All right. Okay, we're just looking at that. And data structures. Here we go. So there's 2D mem, step, gmet. Oh, this is the this is what we're calling in Python. This is at least the function that's being called to create a memory space in the GPU. All right. What other functions are available here? We have gmet, create continuous, CUDA mem, stream. Those are the structures. Do we have any image processing? Here we go. Shifts, integrals, Keras, convolve, warp, affine, resize. Oh, they have a lot of them. Oh, we have a lot of them. We have CV color, threshold, resize, warp, affine. It looks like I could actually utilize CUDA for everything. I'm going to probably have to rewrite it to use those. Let's see here. Where are we here? That's the general image manipulator. We want you. All right then. So warping, I'm using this right here, which is get perspective transformation. Is there a get perspective transformation here? Warp perspective. Yep, right here. Warp perspective. All right, yeah. So I think that we can actually, I think I could speed this up dramatically if I just start dumping everything over to the if I start dumping everything over to the GPU. Let's do a quick check. If I do cv2.cuda.get, let's see, that's get device, CUDA enable device counts. Let's see here. Warp shuffle functions. Events. Get device. Reset device. Set device. Target stream. Warp stream. GPU mats. I think that's a function. Oh, hey. They tied everything to GPU mats. There's reshape channels. Download. All right, where's warp? I don't see warp. I see locate ROI, sweep or swap, step. Actually, I'm a bit curious about step. Okay, so I'm guessing reshape and size are the these are the basic matrix calculations. That's what these are. They're not actually the transformations that we're looking for. So let's hop back out here. Is there... Let's see, warp functions. Is there an image transformation section? Naive double. All right, over here. Over here. Let's see what. Let's see. Yeah, it's just image processing, and then we have GPU, and we can access everything. All right, maybe this is 2.3.2. All right. Let's see here. Python, OpenCV, CUDA, image warp. Let's see if the AI will give me a hint. Come on, AI. Be the dictionary that you're supposed to be. Come on, point me to where I need to go. Come on. To perform image manipulations, you can use cv2.cuda.warp find. But we were just looking at that. That's called... Maybe it's in Warp Stream? Doesn't look like it. No. Maybe the documentation is... Well, the documentation is for C and not... It is... You're right, it is for C. So I was kind of hoping that it would have been translated over. The best thing to do is just try. Yep. Does not have that attribute. So it is... So yeah, even this telling me how to do it is wrong, I bet. Oh, actually, that's capitalized. Let's try. Boom. Yes, it does not work. It doesn't exist. What? Actually, what version am I on? Let's see here. We're currently on 5. 5.00. Okay, then. OpenCV, Python, CUDA. I kind of wish that this would actually tell me where where this is downloaded from. Because, yeah, if I could find the documentation, it would actually make things a lot easier. Pip install Python with CUDA, then we can OpenCV, print, and then we can see if that exists. Oh, actually, question. If I do OpenCV, is that actually, yeah, it's right here. Though I don't know who is. Why is it always such a? Anyway. Why don't we just do this? OpenCV Python. That one. So here it is. Okay. So yeah, this is the maintaining group that I'm currently using. This is the one that I downloaded. So which version is this? Or we know what version it is. It's 5.00.93, but what is the CUDA version? Documentation. Oh, here we go. Documentation. Documentation, manual build, sources, licensing, releases, development builds. CUDA, here we go. Check the manual build section if you wish to compile the bindings from source and enable additional modules such as CUDA. Wait, does that mean I'm not? Wait, does that mean my build doesn't have CUDA? But that would be strange if it didn't, because it should throw an error. Alright, well, I want to find where's the documentation here? Look, if I have to start digging into the functions, I will. Let's see here. Here is OpenCV. Alright, so this is the OpenCV Python. There's the build back end. Here's the CV scripts. There's the wheel. This is just everything that we read previously. And this is the documentation. It's probably going to send me to... How much do you bet it's going to send me to, let's just wait. Let's wait and see. Oh, of course, not page not found. All right. Okay, here we are in OpenCV. Why is it? Oh, here we go. Here. Using CUDA GMAT with trust. All right, perfect. Okay. And we see nothing but C. How did I know? It's sending us to C code. One option would be to just start having writing our own little interpreter area, and instead of just trying to call Python or OpenCV and Python, we just start passing all of our variables into C. I thought that this is what the OpenCV Python was supposed to be doing. All right. Let's see here. Let's see here. I'm going to go here. We're in the init now. CV typing. Here's gmoot. Actually, let's do a quick search here. Warp. Warp size. Okay, then image. I have a feeling that that's not here. And gave up, thought it was added. I see, I see. Oh, so you were in the exact same you're in the exact same boat as I'm currently in. You would think that this would be handed out, or they would have included this by now. I'm a bit surprised that it's... I wonder why it's not here. It is very confusing to me. I see copies and sets, and then a lot of typing, scalars. It is. Especially, I mean, this is one reason why I was looking at Pygame at one point. There's a module called, I think you might have heard about it, it's called Pygame. And what this is, it's pretty much a, very green, but what this is, it's pretty much a Python module for developing games. And you can do all sorts of things here. You can load up events. You can set up like key presses on how you're going to do certain things. It should even have its own, yeah, here it is, image and draw and such. So you can draw graphics on it. Here you go, loading images, saving images. I bet it might even have a ability to process it, I bet. Let's see here. Busy doing a quick peek through here. Image to string, image to bits. From string. From buffer. Alright, it looks like it's just kind of loading images right now. Image draw. Well, okay, you get the idea. The point is that I originally was thinking that maybe I would end up using this here as a way to set up my avatar. Because I remember making a Snake game using it. Yeah, I remember trying... Back then, I was trying to make a visual novel with this, and I did a little bit, but then I gave up. Largely because I kind of lost interest in continuing the game. But yeah, I remembered it and thought, oh, I could probably use this for making... I could probably use this for making my avatar, because then I could have all of the memory buffering and a lot of like image asset loading and such all just done there. It's so slow. Oh, that might be why I gave up. I don't remember why. I remember dropping it at a certain point. So maybe don't use Pygame. Oh. Actually, this is kind of why I was hoping of using OpenCV. Let's see here. OpenCV, CUDA, Python, Perspective Warp. To perform it, you do... Yeah, that did not work. Oh, PyImage search. Perfect. Give me the examples. Wait, how long is this? Let's see here. When was this article done? 2014. Oh, this is actually a fairly old one. I'm a bit surprised. How much do you bet it's not going to have anything to do with CUDA? I used to go to this website for it when I was learning image Yep, no CUDA. I used to go to this website all the time when it came to image processing. And then this is all C code. Oh, got it. the bot is smushing together. Oh wait, here we go, some Python code. If device is CPU, do this. Otherwise, do this. Yeah, this is not, you're not helping learn OpenCV. Okay, then let's see here. CUDA. Well, this entire thing should be CUDA, so why don't we do warp, image warping. Let's go all the way down. Actually, wait, is that the only time that they mentioned warping? Supported modules, image warping. Yeah, I think, I really think that we're going, I don't think, I was hoping that I would have had a good way to go, but I'm beginning to think that I can't do this. I don't think that, I think I might have to try and start sniffing up a different alley. Oh, GPU pipeline. GPU. Here, go GPU pipeline. So in Python, CUDA mat, file size, frame size, okay. Processing other frames. So here we can do a resize. Convert to gray, okay. Calculate optical flow. Actually, one thing I'm a bit surprised about, because back when I was working with a programming language called MATLAB, MATLAB is a, I think this was the programming language I actually first started learning, because in a lot of academia, they tend to use this programming language, MATLAB, for doing all sorts of things, like programming how, if you want your microscope to be functioning a particular way, you'll program it in MATLAB. You want to generate a database that will also do image processing, MATLAB. So I ended up doing a lot of programming in MATLAB. And this was way back when, before they started even considering using GPUs for doing things like image processing. And I remember when they introduced it. I don't know if I can find that code here. Okay, I don't know if we can find the code, but the way that they ended up doing things, which is kind of what I was hoping that they would do in Python, was... okay, let's hop down here so I can show you what I'm talking about. So in MATLAB, what you would do is you would have it called GPU ob, like GPU object, and then you would simply call it their function. I forget what those... Oh, they changed it since then. I don't remember what the function is called, but you'd effectively create a matrix called GPU. You'd something like GPU mat, kind of like what you can do right now, and then you would pass in your variable. So I would have, this would be called, you know, MATLAB matrix, and then you would then put in your particular matrix, which would be, you know, whatever you wanted. Then you would pass that into the GPU, and then from there you can then have, you can then do GPU OB, and then if you wanted to do something like math calculations, this times 2, and then it would do it, it would understand what it was going on, and it would put it all, it would run it all in the GPU. So as long as you interfaced with this GPU object, MATLAB, any calculations, any mathematics you would perform, it would immediately do it over there on the GPU. And then afterwards, you would then simply, it would be a kind of like what you do here as well. You would GPU or GPU ob.get, or, and then you can then proceed to pull it back out from the GPU. I was kind of expecting Python to be doing something quite similar to that. I was kind of under the impression that maybe instead of hey Giovanni, how's it going? But yeah, I was under the impression that instead of like what I'm doing here, where yeah, like right here, my auto cropping. This is currently an image that is being stored on the CPU. I kind of thought that the GPU processing, I could just simply give it this calculations and it would process it for me. It would on the GPU, but apparently that's not the case. I have to actually call it. Actually, that also might explain why MATLAB was a bit slow in certain areas, because it seems like there's a lot of back-end stuff going on to make sure that it understood what you were typing. But that means if I want to do calculation, I probably could still do the overlaying on the I could probably still do the overlaying on the GPU here. It would have to hard code like 8-bit and such. Yeah, right now what we're trying to do, Giovanni, is we're trying to figure out how to use CUDA with OpenCV. Because apparently you're capable of doing it, but yeah, apparently it's very limited, which kind of sucks, because I was kind of hoping to be able to do full-on crazy image processing stuff. Maybe there's actually no real point to last time we were talking about. Oh, congrats. Yes, last time we were chatting, we were complaining about the market. It's good to hear. Glad to hear that it sounds like you're getting an interview and you passed through the first one and you're going to another one. Oh. In Cantonese, here in Hong Kong, they have a saying. It's called, the way you say it is Gai Yao. I can give you the horrible English. Let's see here. Gai Yao. Yao. I wonder if that will work. Yeah, something like that. Gai Yao. Yeah, oh, here you go. Perfect. Gai Yao. No, we don't have to. Yeah, that one. Gai Yao. It pretty much means add oil. And it is a phrase to say to people as in, work hard, work hard, hope things go the way you want. So, Gai Yao, add oil. Yeah, there you go, add oil. Right here, it is a phrase of encouragement and support. We actually found it. Oh boy. My horrible English translation, and we actually found it here. All right, let's see here. Now I have a question here. Let's see here. Python pass C++ instructions. Yeah, I have been applying. I found that there's been a couple jobs recently available, so I've applied to them, and I'm waiting for them to hopefully respond. I don't know how much. I don't know though how much I have. We'll see. The last one I looked at, they said it had over 100 applicants. So here's the hoping it will work. Let's see. Python can execute C++ code by calling compiled C++ functions through extension modules, or bindings like pybind11 or a CPython C API. Okay then. Import spam. Spam system. Oh. Let's not do that. Let's not spam anything. PyObject. This is the Python documentation. How about we go to Real Python and see about what they say here? Because if I have to, I will write a I'll write my image manipulation stuff in C++, and then just pass all of my stuff into that and then pull it back out. If that's how I have to do it in order to use CUDA, then I will do it that way. I just need to know how Python, here it goes, ctypes, pathlib. Yeah, I just need to know how Python does, with the code. Float, that's this, let's see here. Clib, cmult, xy. From, alright then. Oh, okay. Okay. Let's get our reading. Let's start reading through this stuff. Setting up the environment. We need C++ installed. I have that. We need Python 3. Greater than that, yes. We do have a virtual environment. The invoke tool. What is the invoke tool? Invoke is a tool used for you'll be using to build and test your Python bindings in the tutorial. It is similar purpose that make, but uses Python instead of makefiles. You'll need to install invoke in your virtual environment. All right. Well, let's first figure out and see what we can do here. Note that you'll be looking in the tasks Python where you'll invoke defined. Second, however, the output from list shows as this. For each tool you'll examine, you'll be build task. For example, to run the code for CFI, you could type invoke build CFFI, test CFFI, an exception for C types. So C source. So here is our float, which is cmult. This is C multiply. Then we're going to simply generate this and return it. So that is our C code. The functions are mostly identical with minor name and string differences. All right, so C types, how it's installed. One of the big advantages of C types is that it's part of the Python standard library. It was added in 2.5. That is really old. I mean, 2.7 has been discontinued for how long? I haven't heard 2.7 in forever. All you need to do... Okay, all of the code to load your C library and the function. Call a function will be your Python program. This is great since there are no extra steps in the process. You just run your program and everything is taken care of. To create your Python binding in C types, you need to do the following steps. Load your library, warp some of your input parameters, tell C types to return type of your function. All right then. Oh, you use Ma. I just saw that. Hey, are you... Giovanni, are you from Hong Kong? Many Hong Kongers use Ma at the end of phrases. Makes me curious. My wife uses Ma all the time. It's a particle. Yeah, it's a particle that's used to... You use it for a lot of reasons in Cantonese, but anyway. If we want to go into learning Cantonese, we can hop into that. For right now, let's continue with this. Let's figure this out. So ctypes provides several ways to load a shared library, some of which are platform specific. For example, you'll create a ctypes.cdll object directly by passing in the full paths to the shared library you want. So here's Python code. Ctypes and pathlib. If name is main, then what we'll do is we will pathlib path absolute / lib mult so, then ctypes cdll libname equals clib. This will work for cases when the shared library is in the same directory as your Python script. But be careful when you attempt to load libraries that are from packages other than your Python bindings. There are several details for loading libraries. So here we go. Remember that the function prototype for your C function is as follows. Float cmult int. You'll need to pass in an integer and a float that can expand to get the float returned. Integers and floats have native support in both Python and C, so you expect this case to work for reasonable values. Once you've loaded the library into Python bindings, the function will be an appropriate attribute of clib, which is the cdll object you created earlier. You can try to call it like this. Oops, it doesn't work. This line is commented out in an example repo because it fails. In an attempt to run with the call, then Python will complain with an error. Wow. It looks like you need to tell ctypes about any parameters that aren't integers. Ctypes doesn't have any knowledge of the function unless you tell it explicitly. Any parameter that's not marked otherwise is assumed to be an integer. Ctypes doesn't know how to convert the values. 2.3 starts 2.3 that's stored in y to an integer, so it fails. To fix this, you'll need to create a cfloat from the number. You can do that in the line where you're recalling the function. ctypes.cfloat y. Now, when you run this code, it returns the product of the two numbers you passed in. And then we invoke test ctypes. Wait a minute, 6 multiplied by 2.3 is not 48. It turns out that much like the input parameters, ctypes assumes your function returns an int. In actuality, your function returns a float, which is getting marshaled incorrectly. Just like the input parameter, you need to tell ctypes to use a different type. The syntax is slightly different. This is going to be very complicated if I try to use this to because this is just basic integers. I wonder how it's going to work when we start passing matrices around. That is maybe. Okay, I want to check something out. Does Pillow have CUDA? Does Pillow make use of GPU instances? No, there is no support for CUDA in Pillow. Okay then. Python CUDA image transformations. I'm not the only one who's had this problem. There has to be a bunch of people who are wanting to use CUDA for transformations. I can't be the only one who wants to do this. Hey, Numba. Oh, well, I don't... Let's see here. I was hoping to leverage... well, let's not worry about Numba. Numba is a it is a package you can install in. So Numba is a package you can install in Python, which converts your code into C code. It's kind of like you write a algorithm, or you write calculations. You then attach @numba to it, and it will convert it to, here it is, numba.jit, which will then convert this all into C code to speed things up. Hey, Challenger Explosion, thanks for the follow. How's it going? So yeah, if you want to tend to speed things up dramatically, use numba.jit. Be warned though, it might not work with a lot of things, especially if you're trying to do something far more advanced than basic calculations. Because I tried to do this with one of the projects I was working on. We needed to do a lot of matrix calculations, and because of that, I was pretty much trying to do a lot of matrix calculations. I guess that's the best way to just keep it simple. And Numba crapped the bed. It ended up something that should have taken like 2 minutes. It took 10 minutes when I put it in Numba, and I don't know why. It's very strange. I think it was because it was having a trouble with the translation. Doing well, doing well. We are trying to figure out how to use CUDA in Python. Oh, hey, here we go. I wonder if this will work. Yeah, we're trying to find out how to use CUDA in Python because I want to use it to do transformations. There's a lot of so what I'm trying to do here, if you look at my avatar, you can see he kind of bounces around. I can have him look at the screen, I can make him dance. Look around. Oh, very shocked. Oh, very, very shocked. I can have him do a lot of things. To do this, I ended up generating a lot of movies, and these movies are constantly being run in the background, which is taking up an awful lot of processing power. And I figured it would make more sense for me if I wrote a program which would allow me to convert my images directly into a stream for making the avatar. And that way I could end up doing a lot more advanced things than just static movies. As for CUDA being it is used for AI training. CUDA is basically, to keep things simple, CUDA is used for matrix calculations. If you have a matrix and you want to do a calculation on it, you can pass it over to the GPU, which is basically a matrix calculation machine. This is one reason why everybody was nabbing up and buying all up the GPUs when there was the big Bitcoin boom. Everyone wanted to do processing. All of the Bitcoin processing was a bunch of matrix calculations, so GPUs. And because image processing is also a bunch of matrices, I mean, if you look at some of my code here, actually, well, yeah. All right. Yeah, you know what's going on. So because of that, I'm trying to find a way to transfer all my images. I need to open my door. All right, I'm trying to transfer all my images over to the GPU so that I can then start doing all of the calculations. I can start processing my images. There's a lot of different things I need to do. For instance, I need to overlay all of the individual images. I need to change the colors of the images. I might even need to warp them. For instance, making my character bounce up and down when he talks. That is something that is that's something that needs to get done. And if I can do all of this on the GPU, which will speed things up, that would be great. I'm streaming right now. I'm streaming on many different places. I'm on YouTube. I'm streaming over on YouTube, and I'm streaming over on Twitch. Yeah, I don't know why, but for some reason the stream over on Kick, it always fluctuates, so the quality tends to fluctuate a lot. But yeah, if you go to YouTube, you'll find it. It should be... Let's see here. Actually, what is the name of my channel? I forgot. Nope, that's not it. Let's see here. What is the name of my channel? I think it's Curious As You Go. Yes, Curious As You Go. There we go. If you go to Curious As You Go on YouTube, you'll find that. Hey, look, transform.rotate, drop shadow, round corners. This looks like they have a lot. They have transform, blend. We should probably dive into here and see. Let's see here. Pi image CUDA. Let's see here. I see OpenGL. This is like an OpenCL, OpenGL.gl. I wonder if this is I can use this. Let's see. Where's the repository info? That's what I'm looking for. No, no, no. Ah, here we go. Perfect. This is what I want. Aha, this is what I want. Okay. This is what I want. This is what I want. Let's see here. Now let's go digging into the code. No, 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 nope, nope. No barking. No barking. Come on, lay down. It's 6:30 and my dog is like, no, it's time to play. Oh my, they don't have many functions. Oh, I thought they had a lot more than that. They have resize, transform, and interpolate. Okay, why don't we check up OpenGL? This is interesting. I'm glad it's fun to see someone generate this. It feels like more of a proof of concept than a actual library that people can use. I guess so. I guess. I'm now patting him. I hope he doesn't have any knots in his hair. I have a poodle here. He's a little toy poodle. And he's a messy thing sometimes. I try to keep him clean, but he loves to make a mess out of himself. So sometimes he'll get a knot in his hair, usually behind the ears, and if I pull the knot on accident, he'll yelp. He's learned that if he wants to... He's learned that if he yelps, whatever he doesn't like immediately stops. So if I'm like, okay, time to do your nails. I need to clip your nails. He's going to yelp. Like, oh, okay, I guess we're going to not do the nails right now. Like, oh, he needs a bath. He's going to, like, he's a nuisance. That's what he is. He's a nuisance. He wants to play. He keeps giving me his little toy. And it's in my hand again. Let's see here how it works. So, let's see here. Importing everything from OpenGL, which kind of is a bit annoying, but alright. So, make current window, swap, buffers. We need to go to the OpenGL library. Let's go there. OpenGL, here we go. High Performance Graphics Library. No, please don't bark. This is a shader language. You don't have a dog. Dogs can... I enjoy taking care of my dog. He's a funny boy. He likes to do silly things. The bigger one likes to eat carrots, so Sometimes she'll bother me and go, "Oi, can I have a carrot, please?" I would love a carrot. A carrot would be delicious right now. Oh. You better not. Don't shake it too hard. He's gonna smack his head over into something pretty soon. Anyway. Let's see here. Where is our documentation here? Here we go. Get started with OpenGL. All right, OpenGL, what are you? We are going all over the place. Nope. Stop. No. No bark. No barking. Come on. Nope. It's an animation tool. I'm trying to animate my avatar. It's going to be an image to video pipeline for effectively the idea is that I generate a bunch of images and then it will auto create videos. Yeah, I'm beginning to think that OpenGL might not be it either. I might have to do my own. Let's see here. Okay, how about, let's see here. Python, CUDA, image processing. Let's see here. It's a raccoon. It's supposed to be a raccoon. Oh. It's supposed to be a raccoon. I know it kind of doesn't look like a raccoon exactly because the head isn't too... Yeah, the head isn't too squished, but yeah, it's a raccoon. If I had him have to take the VR headset off, then you would see the markings easier. CUDA image processing app, light object. Real-time image processing. Oh, here. Cartoon effect, Gaussian effect to text. These are all filters. Clean Pygame based interface. Okay then. When were you last updated? 10 months ago. Real-time GPU accelerated image processing with Python. Features 11 visual effects. All running at 30 FPS with live webcam input. So apparently the person who made this was interested in making backgrounds for when they're communicating with people. Well, it might be open source eventually once it's done, but for now eventually it'll be open source. The idea eventually would be that it would be, once it's done, then it could be something that people could take it. So yeah, it'll be open source eventually. I need to first get it out of alpha. CUDA image process. Why? It feels like there's a ton of different CUDA image processing sites. I really think that, yeah, I'm really under the impression that this is just CuPy. I think this was mentioned earlier, wasn't it, in the stream, wasn't it? Let me see here. Let's go back a bit. I remember it was being mentioned. Yes, right here. CuPy. All right then, so let's see here. Nope. How'd you get? Go on. Get out. Go on. Out. If you're gonna bark, go on. Out. Hey, SciPy. Okay. Easy to install. Go lay down. Come on. Go lay down. Come on. Here. Look at it. I threw the toy out and he's... Come on, go get it. Good. Okay, he's out. No. He's trying to open the door. I might have to stop streaming in a minute. The dog's being silly. All right, let's see here. So, n dimensions, transformations, mathematical functions, signal processing, memory hooks. Maybe I can probably get you get some use out of CuPy. Hey, JIT kernel definitions, NumPy calculations. Oh, actually, that would be very nice. Hey, Fox on Main, how's it going? We are trying to figure out a way to speed up the image processing code. Actually, maybe I could do... Oh. Maybe this might actually be the way to go. Because CuPy is apparently using the GPU. And if you look, it has a lot of NumPy calculations already. If you look at my code here, for instance, the merging of two images... Oh, come on, don't die on me, computer. I think my computer has died. Okay, there we go. Okay, so if you look here, my overlaying of images, I'm not actually calling any OpenCV calculations. I'm actually performing a matrix. I'm doing matrix math. Here you can see I'm taking the image 2, multiplying it by its alpha channels, so we know what the... I don't know why this is getting very slow. It is getting... I wonder why it's getting tremendously slow. Anyway, maybe if I... Okay, I'm going to go ahead and restart this. Come on. Let's go ahead and... I wonder why it's freezing up. I think there's a... This is one reason why I need to work on the memory. Exit. And this also might be a problem here. We have how many of these open? No, we don't need that open. Jellyfin. Oh yeah, I remember what that is. Okay, we can worry about these. I remember that. I have that already written down. So let's just go ahead and close out as many windows as possible. There we go. And hopefully that will clear up some space. From MS to Linux. Oh, what are you porting? I'm very curious. What are you porting? Are you actually doing a direct, are you writing the code so it'll work more in Linux, or are you using a compatibility layer like Proton? Just automating where you're... All right, I see. Ooh, fun, fun. Okay, then. Actually, you know what? I'm trying to do it all in Python just because I'm being stubborn. But this might actually be the best reason to start getting this programmed in C, especially if we can't even use GPU libraries to do basic stuff. Technically, a lot of my code, a lot of the code that I've generated, is all working, and we've now have set up a format. If you look here, the output. Okay, sorry, not this one. This one. Yeah, if you look here, we now have everything all properly formatted, so everything is nice and tiny. Everything's been cropped. Maybe it might be a good idea to start diving into C++ and Zig and writing this. But yeah, all of my code that I'm doing here for doing a variety of things. For instance, if you look here, colorize. One of the main things I do is I change the color depth. So here I grayscale the image. I then set it to float 32. I then multiply by the color. And then I set it back to RGBA. And then I reset the alpha. So this is how I colorize an image. And by doing it this way, this is kind of the way that a lot of programming, like GIMP, and this is kind of how GIMP does it. So I figured, why not follow what GIMP does? So if there's a better way to do it, then I will have to look into it. But yeah, and if you look here, overlaying images is just doing basic math between the two arrays. Resizing, I actually do call the resize function here. But this is because of the, I need to do the interpolation. Otherwise, I could just forget about that. If I had a GPU that could run AVX 512, then I gladly would. Oh, actually, it reminds me of something. I wonder. Oh, yes, you're right. You're right. You're right. It is CPU. It is the Intel. Intel had released a CPU, a very fast one that had these instructions. I was about to comment because I remember there's. I think RPCS3 has it, or at least it did have it. It doesn't do it anymore. Okay. Yeah, I guess what I kind of thought. Because I remember... It goes brr. I remember... because RPCS3... So RPCS3 is a very powerful emulator for running PlayStation 3 games. Let me head over here so I can show you. We talked about it last time. Yeah, this guy here. This is an open source PlayStation 3 emulator. And for those who do not know about the PlayStation 3, it was a giant pain in the butt to program. Yeah, actually, this does the compiling for you for the PPUs. In fact, this is actually one of the main advantages that AVX 512 had. Because apparently... all of this is being done through the CPU. I mean, there's a lot of stuff that's being passed over to the GPU, especially when it comes to the graphics side of things. But a lot of the compiling for like running the PPUs and setting those up and running them, it was all done on the CPU. And because of that, if you didn't have a very fast CPU, then you're not going to be running PlayStation 3 games very quickly. And one of the fun things was that AVX 512, it actually dramatically improved the speeds of the frames per second for the RPCS3. So for a while, when they had that here, so let's go see if they, let's see if they have this here. No, it wasn't that... Here, there's someone trying to argue why it's useless. It actually helped speed things up. It made things a bit more efficient when it came to running the PPUs. It's better than the Windows version because Windows can't sleep the cores. Yeah, I know. That is one of the big problems I've been having. Because I have a... My computer is not fantastic, but it's good enough to run the RPCS3. And there are certain games where you have to allow the cores to sleep, and if you don't, then it just crashes. So there's some games where people have been talking about them, saying, oh, this game is great to play. And I'm sitting there thinking, yeah, it's great to play on my PlayStation 3, but when I load it up in RPCS3, it keeps crashing. Look at this block. Is the main... Okay. Oh. All right, let's check it out. Often said that let's check it out. Let's read this real quick. We are getting distracted. Let's see here. It's often said the importance of difference between instruction sets of modern computers is overblown. It's hard to actually disagree with this observation. Since 90% of the average program is made up of basic ALU instructions, load and stores, and branch instructions, and given the fact that the gap between different instruction sets is very small in terms of these basic instructions, it's easy to agree with this conclusion. But the PS3 emulator, RPCS3, isn't an average program. Even if you haven't used the emulator itself, you may have heard RPCS3 brought up as an example of consumer software that can take advantage of AVX 512. In this blog post, I will cover why exactly the new instructions and features introduced in the AVX 512 family are so useful for PS3 emulation. In some situations, use of the 512-bit instructions can be profitable for RPCS3. But in this post, I'll be covering why the new instructions introduced are useful at 128 and 256. My dogs are going crazy. Go. I'm trying to read something. Come on. So, large register family. The AVX 512 instruction set comes with a register file 4 times the size of the AVX2. The registers are doubled with width from 256 to 512 bits, and the number of registers available to the program have doubled from 16 to 32 as well. The PS3's SPUs have a register file of 128 individual 128-bit wide registers. It doesn't include any general purpose registers like the typical CPU, and even memory addresses will live in these registers, despite the fact that I am fighting with my dogs. Come here. I'm going to hold on to you. Please stop making noise. Let's see here. Even memory addresses register, despite the fact that the addresses will only use 32 of the 128 bits available. Since the SPUs do not implement register renaming or out-of-order execution, it's essential that loops on the SPU are uprolled to actually take advantage of the 2 execution pipes available on the hardware. Since an unrolled loop on the SPU may use upwards of 60 registers, this poses a problem for emulators. The solution is to spill out registers to memory when too many are used to fit the host CPU's registers. But this comes at a cost in terms of performance. An extra registers introduced in AVX12 might help mitigate this issue, though they don't solve it either. Let's see here. AVXQ doesn't just add new instructions, it also adds new encodings for old instructions as well. Many instructions which supported a memory operand now support the embedded broadcast feature, which allows a 32 or 64 value from memory to be broadcast to all elements of the vector before use. Another useful feature in the new encoding is the DISP-8 compressed displacement. In normal architecture, the 8664 instructions are embedded displacements can be encoded in just 1 byte if the displacement is between -128 to 127. If the displacement exceeds this size, a full 4-bit displacement is required in the encoding, even if the displacement is still relatively small, like 256. With DISP-8 compression, the displacement can be encoded with a single bit if the displacement is a multiple of the vector size, and the multiples between -128 to 127. For instance, the displacement of 256 for a 128-bit 16-bit vector encoding would encode as 16 times 16. Unfortunately, the new EVEX encoding requires another bit, and the VEX encoding instructions, so only 2 bits are saved over a VEX encode instruction. Alright, this is quite dense. Let's see, let's go down real quick and see, because he is going to explain all of the information. So Let's see here when he starts talking. Here we go. It turns out that SPUs inherit a bizarre floating point format that the PS2 used. This floating point format does not support NaN, not a number or infinite. He has videos on the topic too. We might have to watch that. I might have to watch that because I'm very curious. He's actually talking about the PS... Oh, hey, PCSX2. Another emulator. Actually, to try and not go off topic while being already off topic, I just want to say that I'm happy that the PS2 has been getting a lot of love. Originally the PSX2, while being a great emulator, the code base was a bit dated, but that's largely because it was made like 20 years ago. So it was actually very fun to see that it had gotten a lot of updates recently, and it has Vulkan support now, and it's PCSX2 is really one of the best PlayStation 2 emulators out there. Let's see. It's good visual. Oh, that's funny. That's funny. It's quite difficult to get rid of... Okay, so let's see here. When browsing through the SPU, the public SPU via documentation, there's a curious little paragraph about something the documentation calls extended range floating point format. What in the world is an extended range floating point, and what do you mean by game applications assume a single precision floating point format that is distinct from the IEEE 754 format commonly implemented on general purpose processors? It turns out that the SPUs inherit a bizarre floating point format that the PS2 used. This floating point format does not support NaN or infinite, and instead interprets these values as very large floating points. Once a NaN or infinite value is generated, it's quite difficult to get rid of most operations after will return NaN or infinite. For instance, infinite times 0 equals infinite. Infinite times -2 is negative infinite. NaN times... well, yeah. The only way to accurately emulate this behavior is to re-implement it in our own software floating point implementation. Unfortunately, software floating point is incredibly slow. So RPCS3 does not, at this point, have software floating point emulation of extended range floats, referred to by RPC3 as XFloat. Yeah, that does remind me. One of the biggest problems for Nintendo 64 emulation was the microcode. The Nintendo 64, so N64 microcode. So the Nintendo 64 used... oh. Sorry, hey, welcome back. Welcome back from ads. I hate ads. Okay. So one thing that the Nintendo 64 had that the other... So, alright. One moment. Okay. The Nintendo 64 could use something called microcode. The microcode are these basic functions that you could use in order to tell the... It is basic scripts that you could write for the N64 to run and do particular things. A lot of games ended up utilizing it later on, which allowed it to do lots of things, but because of the fact that these are all unique for each individual game, they're not standardized. What ends up happening is a lot of games that reuse microcode fail to run on the Nintendo 64. And because of this, for the longest time, you could not get accurate Nintendo 64 emulation. The only way to do it is as if you wrote or implemented if you implemented the microcode, or you had to pretty much do software emulation, which would emulate all of the bus, or what are those things called? Where the microcode was run, you would have to software implement it, and it would get fully accurate N64 emulation, but it was at the cost of having a very slow running emulator. And it seems like this might be something quite similar going on here. I see. I see. Yeah, yeah. This is actually what I'm pretty sure that he'll start getting into that. Um, a relaxed X float, approximate X floats. Because having the extra long memory buses would probably help out a lot. Hey, here's the performance thing. What does it all mean for performance? There you go. The performance when targeting SSE2 is absolutely terrible, likely due to the lack of a PS Hub F instruction in the SS3. PSF Hub is invaluable for emulating the S shelf B instruction, and it's also essential for bit swapping vectors. Something that's necessary since the PS3 is a big Indian system, while XE4. Whoa, that's also, I did not know that. A big Indian. Hey, Electric Splash, how's it going? We're busy learning a bit about AVX 512 and how it helps the RPCS3 work. One may wonder why it's worth targeting such new instructions. That's for the newest, the fastest processors that support these instructions. After all, even when targeting SSE 4.1, it's available to produce playable 160 FPS. However, not all CPUs that support 512 are 8-core monsters clocked in at 512. Most CPUs that support AVX 512 today are either server CPUs or laptop CPUs. Wait. Alright. Since Intel had problems ramping production of their own 10nm processing, Intel chose to first release their new A512 supporting pipeline of processors on laptops, which can get away with smaller die sizes. The use of the AVX 512 on these lower laptop chips isn't going to push performance into the 20 milliseconds, but it does do does it for giant 290X. The Zen 4. This is actually a pretty good read. 2022. Okay then. So yeah, this is a little bit old. Oh, stop. Yeah, this is 4 years, and you said that 512 was being discontinued, wasn't it? Okay. Let's see here. It's the 512-bit extensions, instruction sets, encoding, sim modes, the new instruction sets. We're looking for the implementation. Come on, where's implementation? Come on, where are you? CPUs, here you go. CPUs with this. There's the ones for Intel, AMD, ooh, and Zen, oh wow, okay. So, it looks like, alright then, so it looks kind of like AMD is going to be the ones that are going to be using AVX 512. The Intel little core big core setup fails to be able to do it unless it disables the E-cores. Doesn't it feel like Intel is just having lots of problems? I'm rooting for them. I hope that they'll get back up on their feet, but I can't help but feel like Intel just... They're at the point where they're going to be left behind. It really feels like it. Like, man... AMD seems... I know that when I eventually buy a new computer, when the current one I'm using, eventually it decides to kick the bucket, I'm definitely going to go with AMD. It runs at a... Actually... Oh, actually, to be fair... I'm just looking at the specs on my computer right now. I have a Ryzen 7. So I already have an AMD computer, AMD. I already dropped Intel. Ah, poor Intel. You have AVX2 then. I wonder if I'm going to have to check the reason why I got this computer. No joke. The reason why I bought this computer here, this was how many 10 years or how many years ago was it? Oh, how many years ago was this computer? Oh, actually, I was just about to mention that. The reason why I have this computer is because I wanted to run RPCS3. That is the exact reason why I bought this build. I went out there and I found a graphics card, and I went and found the Ryzen 7. It was a particular card rendition because apparently there's a certain, for a short while, the AMD graphics cards, or sorry, the AMD CPUs, one of them was better than it was better for running PS3 games than the newer models. So I purposely went and found an older Ryzen 7s just so that I could make it work better for RPCS3. Oh, okay. Oh, hey. Hey, yeah, we have a... Yeah, I believe on the left it is Twitch, and on the right it's YouTube and Kick. Granted, sadly, Kick is not having much luck when it comes to the bitrate, but this is the better side. Hey, oh, we're having a side war now. I did find out that one of the things that I'm using, we can figure it out later. I found out that one of the things that I have, it keeps track of which side is communicating. And then I thought it would be kind of fun to like make have YouTube versus Twitch battle, but I need to get it working more. Anyway, yeah, the computer I have is purposely for running RPCS3, and and I've been actively doing it. I think we looked at it last time actually. There's one game okay, let's look at this real quick, and then I'm going to get back to my trying to figure out CUDA. Let's not get any more distracted than we currently are. Let's see here. I am looking for Zone of the Enders. Here we go. Zone of the Enders, second runner. You're right. I remember looking at it. I never activated it though, because I was under the impression my computer didn't have the capabilities. Let's see here. Here we go. 2020 was the last time. So yeah, this computer is about 7 years old. It's about 7 years old. Hey, here we go. I have a Ryzen 7 380X 8-core processor, 16 threads, 16 gigs of RAM. It's an AVX Plus, and then the operating system is Windows. Yeah, it's not going to be Windows much longer. And then I was running version 0.012 of this build right here. It is, see, Ryzen 7. No, I didn't say 7000. I said Ryzen 7. I said Ryzen 7. It's not a 7000. You had to find your Twitch. Oh, on Twitch it is HK Stash Panda. Oh, sorry about that. I need to speak more clearly. It's a Ryzen 7 380 or 3800X. I didn't know that Ryzen 7 had a 7000. But yeah, I ran. Yeah, I ended up running this because I wanted to. Look, I have Zone of the Enders on disk, and I'm like, I want to play it on my computer. Damn it! I'm going to play it on my computer. There's a Ryzen 9000 and 10000 and then expected early next year. Oh, wow. Oh, wow. Oh, wow. I am very far off. Oh, I am very, very... Well, this computer is 7 years old. So, anyway. It is 7 years old. Okay, we want to go back to Kupai. Kupai. Let's see here. Particularly, we want to see about... Here we go. Import Kupai. Then we go CP, arrange, reshape. Highly compatible with NumPy and SciPy. Kupai's interface is highly... Wait a minute. I remember this. I was trying to use this back then because I was trying to speed up some of my matrix calculations. One of the big things was that it was like a plug and play. Instead of using NP, you just changed it to CP. Actually, that means that I might be able to... Actually, that means if we can just transfer all of our calculations into... Because what... Yay, found it. All right, I'm glad you found it. Yeah, because one of the things that we're doing is... Okay, first things first. Let's see about installing Kupai. Here we go. All right, let's go ahead and install that. Let's see if it crashes and burns. All right, while we're doing that, what we want to do is look up Python NumPy or perspective transformation calculation. Because it's all basic, it's all math. It's all math. No, we don't want OpenCV. OpenCV is just doing math. What's wrong with my perspective transformation coefficient? Here we go. Oh, okay. Well, I'm going to have to change this to dark mode, aren't I? Appearance. We'll worry about it later. Let's just go ahead. I'll worry about it later. But yeah, here we go. This is what we want. Let's see here. Why would you do this without NumPy? You have to be working the NumPy version of the code. So if you tried some product flatten, it's a huge detour, but it is for a pure Python experiment I'm writing, in which you pure Python imaging library. Actually, we might be able to take advantage of that. 2 CPUs next year. Sounds like something Apple would do, but for the iPhone. That would be interesting. Actually, there's a lot. It's very fun to look at the technology and see how things are progressing. I'm very curious about. Because apparently there's been a lot. Let's see here. What are they called? I'm just gonna let me just type in what is associated with. So AI hardware. It's a special type of hardware that's being developed, purposely designed for running AI. I don't remember what it was called, though. I just remember that that's what it was supposed to be for. Not Lisp machines. It had a... It wasn't GPU. It was... What is it called? Let's see here. Probably for AGI. Haha. I know that it was something that they were trying to argue that they wanted to put on the motherboards as a way to make it easier for people to, for the average user at home to be able to use AI. It was NPU. That might be it. Let's try NPU. There it is. Yep, there it is. Hey, thank you, Fox on Main. It's not 2 CPU. All right, then. It's a neural processing unit, also as an AI accelerator or deep learning processor. Their purpose is to efficiently execute already trained AI. Oh, wait, that's it? Wait, that's it? Oh. Well, I wonder. NPU applications include algorithms for robotic and data intrusive things. They are often many-core or spatial designs or low-precision. Okay, AI accelerators are used on many different things in smartphones. They plan to use them in data centers. Scientific computation. Although NPUs are tailored for low-precision operations, int8. Actually, that is one thing that I found out, which I was quite shocked about, because TS code. Oh, hey. Actually, who is that? Have to check that out. The one thing I want to comment on is when I was doing training for models and building neural networks, and one of the things I quickly found out was that a lot of the models, they would use these floating point 16s and int 8s. So one of the things I thought of, which would be great to help speed things up, was that I would convert all of my variables into int 8s or float 16s. Like, hey, I'll be very smart. If I convert them to these, then it'll take up a lot less processing. Only to find out that that's actually not the case, because Python, all of it's done, and I think it's not even Python's fault. It's the architecture. It's all 32. So what was going on was it was taking my int 32 or my int 8, converting it up to int 32, and then converting it back down, which just increased processing time. Yeah, as soon as I found that out, I'm like, oh, that's as soon as I found that out, I just had to just change everything to work in 32 and then just save it as an 8 to save space. Oh, TPU. What is TPU? Let's see here. TPU is a tensor process. This is there we go. This is what I want. These tensor processing units. This is it's a lot like a GPU, but instead of being dedicated to just graphics, it actually is dedicated to just processing tensors. What GPU do I have? I have I think it's a 26 or 2600 RTX. Yes, I do. I have tensors already on it. You're right. Hence why I can run a lot of different image. What's the name of that model? I have Stable Diffusion was using it. But yeah, I ran Stable Diffusion here and there. I think these should be more, well, actually, I don't know. Hardware is not exactly a strong suit of mine, so knowing about as you said, it's already, apparently, the tensors are already on the GPU, so I probably don't need something like this. It's just that it's, let's see here. Let me see if I can find it real quick. Where are you? Where are you? Old physics card. I've missed the H. There it is, Physics X card, right here. This is this is a recent thing. Or this is a recent article. Old computers meant to have big jobs. Here we go. Okay, yeah. Oh yeah, ads are so annoying. I'm going to have to see about what to do with those. Anyway, this is kind of what I was... So, as you mentioned about tensors, GPUs apparently have them. I'm not really... Yeah, I'm not very much in regards to keeping up to date with computers. Or hardware, I should say. So, physics is so stupid that it does not work because it's not standard. Yeah. But I can remember back when I built my first computer. This was, first computer I built was back in 2008. And I was actively looking at PhysX cards because I can remember people talking about how you would want to use a PhysX card to... Oh. Okay, one moment. Let me go over here. Let me head over here and see what is going on. That should be allowed. I thought I allowed that. Okay. I know what you mean. I know what you mean. Nowadays, you don't need a PhysX card. In fact, I think a lot of this is kind of built in. I know that they used to... Let's see here. There's a lot of old technology that I can think of. There was this PhysX card, which was used for... It was supposed to be running all of the physics so that you could play Half-Life 2. But I think with GPUs and such, this is archaic technology. And then what was the other one? There was an old graphics card that split the image into two parts to speed up load times, or speed up it doesn't use PhysX. Then what used PhysX then? I know at a certain point let's see here. Where are you? I know a lot of technology. I'm now very curious about PhysX. You distract me. All right. Let's look more into PhysX. NVIDIA made PhysX. All right. I did not know that. PhysX is an open source. It's an open source developed by NVIDIA as part of the Game Suite. It did not make it. All right. Did they? It bought PhysX. Got it. Got it. Got it. Initially, video games supporting PhysX were meant to have accelerated to PPU. However, after AGIA's acquisition by NVIDIA, dedicated PhysX became discontinued in favor of the API being run on the CUDA-enabled GeForce GPUs. In both cases, hardware acceleration allowed for the offloading of certain physics calculations from the CPU, allowing it to perform on other tasks instead. PhysX and other middleware game engines were used in many video games today. Because they allow game developers to save development time by not having to write their own code to implement classic mechanics. Let's see here. During 2001-2003, the physics mediaware market was highly competitive, but technology development looking to implement rigid body dynamics chose between highly expensive commercial packages like Havok, middleware tightly coupled with specific physics engines like Math Engine Karma used in Unreal, and open source solutions, Open Dynamic Engine. NVIDIA X entered the landscape with the solver that prioritized extreme mathematical precision and forward-thinking hardware scaling. The second iteration of the Novid physics was commercially in use. All right. Mafia 2 using it. Oh. Physics and video games. All right, an Unreal Engine, and then there's a handful of physics technology was used by game engines such as Unreal, Unity, a whole variety of things. It is used in many games. Witcher 3, interesting. Interesting. So, it makes it sound like this is still in use. The graphics, the card is no longer around, but apparently sounds like it's still getting or what was developed. The API that was developed is in use. Yes and no. I see. Let's see here. Multi-GPU cards. Multi-GPU is dead, but dual-core PCing is alive. Is this the one that I was looking for? There are better open-source implementations that are hardware agnostic. Ah, I see. Yeah, that's kind of how things go, doesn't it? Eventually, open source beats out. All right. I don't know what I'm looking for. All right, let's just get back to working on this code. Let's get back to working on this. Let's see here. So here's the tilt. Interesting that they created a function to do with more functions inside. Let's see here. Let's just here we go. This one. Yeah, the one that I need to learn or go back and read more history. There's a lot of things that I apparently keep or don't get or think correctly. What do you think? What you are thinking about is the old SLI that had an option to split the screen display in half. However, it was mentally dumb because the complexity of the rendering and stuff is not divided by the screen, so it hurt performance a lot. That might be the one I'm thinking of, the old SLI, because I remember this was one of the new. Back then, in the year of 2000, in the early 2000s, they were trying to find ways to speed up writing to the screen. And one of the things that they had mentioned was if you split the screen in, as you said, split the screen in half, and that way you could have the bottom of the screen rendered, the top of the screen rendered, and then you compile it back together to theoretically speed it up. I think a lot of people said that it hurt performance a lot. I wonder. I'm wondering. Let's see here. Let's type in old SLI. Scalable link interface. It is a multi-GPU technology developed by NVIDIA with 2 or more video cards together to produce a single output. The technology was invented by 3DFX. I haven't heard 3DFX in a while. On AMD, the tech was called Crossfire. I think I remember hearing about Crossfire. Okay. I think I remember hearing about My dogs keep barking. I think I remember hearing about Crossfire. And yeah, didn't know much about it, but I knew about this one. So, hybrid SLI. SLI does not always give a performance benefit. In some extreme cases, it can lower the frame rate due to particularities in the coding. And oh, here you go, as you just mentioned, Crossfire, AMD. Yeah, he's angry that... Come on, how'd you go? He's angry that he heard somebody open a door. But yeah, when I was back when I was building my first computer in 2007, 2008, I was looking at this thinking, do I need this card? Like, do I need to get the physics engine card so that I can, get advantage of physics or take advantage of physics? Do I need to get one of these SLI style cards so that I could help speed up performance? And then apparently, yeah, I didn't have to do any of that. But yeah, because of this, I tend because of lack of knowledge when it comes to certain technologies, I'll sit there thinking, oh, this would be great. Having a TPU would be fantastic because then I can help speed up doing a lot of tensor processing. But apparently, if it's already built in the GPU, then there's no real point to have that card unless I don't want to have to output graphics. Yeah, this failed. Okay, why did you fail? This error originates from a subprocess. It is likely not a problem with pip. Okay. Okay, so why did you fail? The only cards that are external that are worth it is sound cards, now more known as DACs, DACs. I use a DAC that is also an AMP to interface with an... Oh, I see. Actually... Yeah, I can kind of see that. I know that... I know I used to be interested in capture cards, but I actually ended up finding a small little device which... It converts HDMI into a USB output, and then because of this, I can, as long as you have something like OBS, which can take in an input like this, then you can stream all of the, you can stream capture of whatever you want to capture. Oh, that is quite nice. That is quite nice. Actually, that means with those, you could probably get some really good audio output audio with lossless. Okay, so why did this fail? Why did you fail? Output. That's the point. Ah, I see. Yet, you are trying to build SciPy from source, which is not recommended for general use. Please consider using a binary package. Was I trying to build it from source? I just told High charm to install it. I figure that would... Okay, it might be building from source. Please consider using the binary package instead. Oh wow, that sounds very fun. You have to have some pretty good Hopefully you have some really good speaker. Actually, did you... I keep getting distracted. Okay, it's 7:30. I'm going to try and figure out this later. I'm going to wind down because I need to feed my dogs in a minute. So, headphones only. Okay. Let's see here. I used to have a professor who was I had a professor who was an audiophile. He really loved music. So he built himself his own personal sound system. And he did a lot of... He tried to... He built his own sound system. It was a 9.3, I guess you could say. Theoretically 3. He had 3 subwoofers, but it was a 9.1 surround sound. He had 2 speakers in the front, then 2 speakers on the side, then 2 speakers on the back, and then he had additional speakers that would be further behind you. So he tried to surround you completely with speakers. And then he had a very special subwoofer. I'm trying to find the... because he ended up... let's see here, because he commented about this quite frequently. 9.1 is the golden standard now. I see. Oh, yeah, for him, he was building this... Again, this was like 16, 20 years ago. So it's amazing how... things have slowly made up to this. 1 in the center, 2 in the front, 2 in the side, 2 in the back, and 2 at the top. Oh, top. Okay, yeah, his weren't at the top. Interesting. You do know that now that they have center, front, side, back, top, they're going to have, say, 2 more from the bottom. I think 11.1 is going to be the final incarnation, where you're going to have 2 below your feet. And I am not... Nope. No. I'm trying to find his formats. We just have Adobe Atmos as the standard now. All right. I see a lot of smaller designs, but I guess the best thing way to... I see. Oh, okay. I see. I can't find the... I can't find exactly the format, but the way that he used to set it up was... Let me go... I guess we'll go here to try and explain it. So his house, if you look at his house... Oh, I know, I can load GIMP. Let me go hop over to GIMP. There we go, GIMP's here. Perfect. Okay. So the way his house was set up was he had his room right here. So this is his room. He had a projector here, then he had speaker here, speaker here, speaker here, and then here. Then he had another 2 speakers here. The couch was right here. The projector was right here, and the projector had 2 speakers in it as well. Or the 2 speakers right there. So this was his design. And then in the corner right here, he had the subwoofer. This was the subwoofer. Now, apparently, he did not like... Because he commented frequently about it. He said because the subwoofer is usually this box like this, he said that you can end up hearing a lot of reverberation in the box because the subwoofer would be going off, it would shake the box, and then the box, you could then hear that shaking in the back. And he absolutely hated that. So what he ended up doing was he cut bit out of the box. So this was pretty much, this was the subwoofer bit, like this, but it was open on the top. So if you look, it was open. And then all of the different components, you could see the components here. And he put that into the back, into an open room. So the idea was he had this big empty open room, and the subwoofer was kind of fused right into that, so that yes, yes. And by doing this, effectively, it would be you would have zero vibration. So yeah, zero vibration. And he said it made excellent, fantastic sound. You could hear the vibration, or you could hear the effects coming out of the subwoofer without getting the vibrations of it from the box. It was crazy that he set it up himself, and he loved the Bose. He was like, there's only like 11 people out there who have their design set up like this, and most of them are in the UK. He was a very interesting guy. But yeah, it's quite interesting. It looks like apparently there's been a lot of trying to make also these open ones. Because look at this. It looks like they're trying to build a design to decrease the amount of vibrations that will happen. I wonder. All right, last thing to check, and then I'm hopping off. You mentioned Dolby Atmos. Dolby Atmos. Here it is, Dolby Atmos. Dolby Atmos is a surround sound and spatial technology developed by Dolby Laboratories. It expands on the existing surround sound systems by adding height channels, as well as free-moving sound objects. All right. They have built-ins 5.1, 7.1. Differ slightly in the additional. All right then, 7.1.4. Authorized. Enabled speakers are available, integrated in modules, implementation, commercial use. And then here are the, Microsoft no longer bundles with Adobe Digital Plus. Oh yeah, that means that it's not going to, you have to, if the operating system isn't using it, then you're going to have a lot of problems. Dolby Atmos has smartphone implementations, but it's not included in iPhone XS and XR. Almost all Samsung smartphones and tablets released after the S9, they include this. Okay, it's not track audios per se, it's position data and loudness. Yeah, I was just about to comment on that. If it's... That is, yeah, that is, it sounds like if they would actually separate it out into different channels, that would actually make things a lot nicer. I do understand if about distance. Let's see here. Let me hop over to, let's hop back over to GIMP. So yeah, I do, because it reminds me of, some stuff. Oh. Alright, this is fine. Or... Because you would think that if you have multiple speakers like this, then when you're playing your audio, it would actually have 4 different channels, and then it would send them to the individual, to the individual spots. That would make the most sense. And you can have, like, as you mentioned, positional data plus loudness, and then that way in a theoretical environment, if the object is supposed to be here, then you could do a vector calculation and put it down. And then based off of where the speakers are, you could then like, oh, because this is going to be between these two speakers, then we're going to average these two together, give it, try and average the two together based off of loudness and infer this. I'm guessing that's how it's working. And again, it does kind of work, but it reminds me an awful lot about like color, especially monitors. There are, the way that colors are made on a computer is you have 3 pixels and they can be red, green, and blue, RGB. And if you want to make yellow, then you just simply mix 2 of these together. You would mix red and green, and that would generate yellow. Likewise, if you wanted cyan, you would mix green and blue, and it would make cyan. And because of this, monitors can have many, many different colors. Like if we go to, can you guys see it if I click on this? No, you can't. Okay. But pretty much you can get a rainbow of colors doing that by mixing them together. However, a thing to note is that it actually, because that this is a merging of 2 separate colors, it's not actually going to be a true pure color. And because of that, if you wanted something like a pure yellow, you're just not going to get that. You're just going to get a muddy yellow. And because of that, a lot of TVs out there. Let's see here. TV quad color. Yep, here it is. Quatrons. Oh, okay, that doesn't... Is there an image that I can see here? Where are you, my friend? Granted, the technology might not be up to date. I guess that's a good way to put it. It might not be up to date because I'm an old fart, so all of my knowledge is old and it might not be accurate. But yeah, here we go. Aquos LCD TVs. They would come out with an RGBY subpixels. And what this pretty much meant was instead of just red, green, and blue, they would have red, green, blue, and yellow. And they did this in order to get true colors. And then at a certain point, I don't know if it's... they ended up having TVs with 6 pixel colors. They actually decided to come out with all 6 pixel colors. Is it you, maybe? I don't remember which... It was a Chinese TV that I saw last. I don't know if it's ended up going further beyond them. Maybe Google might be a bit better at finding this. Let's see here. Pixel 6 colors. No, that's not you. I have a feeling I might not be able to find this. I'll have to probably look it up later. Red, green, blue has been so standard. Let's see here. TV with 6 pixel colors for color range. What is it? This one, the 6P color? There's an RGB on the display. It might be this one. It might be this technology here, maybe. The main point I'm trying to get at is, in TVs, they acknowledge the fact that there was problems with trying to blend from two different sources as a way to try and, in this case, in the case for audio, they want to try and have full audio range using like the atmosphere. And by doing so, they end up doing distance times loudness, and then they will subdivide it between the different. Speakers, and it works great in a sense that you're able to get what you want done. But it also is not going to be true sound. There's going to be some kind of artifacts there. It's not going to be true audio experience. Having something split completely from left channel to right channel is going to sound differently from you trying to do an area calculation and then average it. Here you go. 6 color sources. These guys. It is the 6P. Okay, yeah. Yeah, TVs are going to get a lot more colorful pretty soon. 6 color tech. Aquos is, Aquos was the one who had the Quatrons, which was the 4-color one. Alright, you better not be lying to me, AI. You better not be a liar. But anyway. I think we've got distracted enough. I'm going to figure out about why this is not working. If I have to build SciPy myself, then I'll see about getting it built. Hey, we have different CUDAs. I need to find out what the CUDA is on this computer. I see a lot of CUDA SciPy. These must be all of the different compiled libraries. Framework for ETLs. Anyway, I'm going to hop off. I need to feed my dogs. My dogs need to be fed. So I'm going to hop off. I'm going to figure more of this out, and we can try and get this working more tomorrow. As I said, maybe I might have to just start hopping over and start using Python or C++. I know that I have Zig installed here, so yeah, I have Zig here. So maybe we can start running, maybe actually start getting involved here and start getting this set up. This will be a whole new can of worms because, yeah, my knowledge is very basic when it comes to this. I think we've probably already had enough fun with trying to learn some of this stuff. All right, yeah. What I'm going to do... oh, I know. Actually, let's see here. If I recall... Where are you? This one here. Okay. I will have to watch this again. It's 33 minutes. Yeah, I'll have to watch this again. It's 33 minutes, but he goes through a lot of different... this is JT. He's the one who wrote NeoVim. Or, well, at least he works on NeoVim. He has an entire guide on how to use NeoVim and a lot of the different plugins. Let's see here. Key maps, LSP, key bindings. Yeah, mainly the key bindings I need to remember. So yeah, I will. Maybe we'll watch this next time, or but either way, maybe tomorrow we'll mess with this. Until then, though, everyone have a good one. I'm gonna hop off and feed my dogs. It's been fun hanging out. I will figure this out here. But until then, laters. Oh, and they're barking again. Laters. My dog loves to bark. Bark, bark, bark. I want to see what the exact error was. Let's let it crash again. There we go. All right, you have a good one, Sora. Laters.